Hello, Mr. Tomashik here. The next thing that I want to talk to you about is temperature. Now, what is temperature? I got a couple videos. I think I'll just put them on Schoology for you. You can watch those. They're kind of short. But when we talk about temperature, there's three main temperature scales that are used in various places around the world. Probably the most common one, or at least for us in the United States, is this Fahrenheit temperature scale. We're most familiar with that. But if you go anywhere else in the world besides the United States and a couple other places, everybody else uses the Celsius temperature scale. And then there's also the Kelvin temperature scale, which is directly related to the Celsius, and that's more of a scientific temperature scale as well. We'll be talking about Kelvin a bit more when we get into gas laws here shortly. Now, how do these temperature scales compare? The Celsius one, which is actually the most common one around the world, has a couple of key points on it. 1, 0, 0, which is 0 degrees Celsius, the temperature at which water freezes. On the higher end is 100 degrees Celsius. That would be the temperature at which water boils. And then when they invented the temperature scale, they realized that you could get colder than that freezing temperature. You could get hotter than that freezing temperature. And then you just divide the distance between 0 and 100 into 100 little increments, and that's what 1 degree Celsius is. Now, the reason why we use degree as a measurement here is because it's kind of relative to some arbitrary spots. So we just sort of pick the fact that, water freezes and call it 0. And the fact that the temperature at which water boils, and we'll call that 100. And then we can go above and below it. And at the time it was invented, no one really understood that there was any kind of limit as to how cold stuff could get or how hot stuff could get. And you just go increments above and below. Now, on the Fahrenheit scale, 0 degrees actually translates into 32 degrees, and the 100 degrees Celsius translates into 212 degrees Fahrenheit. Those are the temperatures at which water freezes and water boils. Now, where was the 0 spot picked then for the Fahrenheit scale? It's still a little bit unknown for sure, but somewhere down here below 32 is 0 degrees, and that was probably thought of as the coldest artificially produced temperature at the time. And you could do that by taking some water, throw in some ice and a little bit of salt, maybe a little bit of rubbing alcohol, swirl it around, and it will get much colder than 32 degrees. So they call that the starting point of 0. And then just like in Celsius, you can get lower than that. And just like in Celsius, you can get higher than that. And the spot that's about 100 or degrees Fahrenheit was pretty close to what they thought was body temperature. All right, now that may or may not be exactly what happened, but there are some arbitrary spots that Fahrenheit picked as the 0 spot and the 100 spot, and then just split it up into equal increments above and below, and so on. Lay the two next to each other, and that's how you compare these two things. Now, again, remember that these scales were thought to not have any limits up and down on either direction. And then later we figure out that there is a limit to how cold something can get. And if you look at this definition of temperature, it's a measure of the average kinetic energy of the particles in a substance, whether that's a solid, liquid, or a gas. Now, maybe recall from 9th grade that kinetic energy is 1/2 mv squared, the mass and velocity of the particle. So if a particle slows down, its temperature also goes down. As a particle speeds up, its temperature goes up. So these two things are connected to each other. In any given substance, a solid, liquid, or gas, the molecules are all moving at different speeds. So that's why we say average there. It tells us something about the average kinetic energy of the particles. And the faster that average is, the higher the temperature is. Now, The question is, what will happen if the velocity reaches zero? Well, then you'd have zero kinetic energy. Well, then by this definition, you won't be able to get any colder than that. So the Kelvin scale starts out at zero, and that's the coldest temperature that anything can be. We call that absolute zero. Now notice when we say 0 Kelvin, we don't put a degree symbol behind it because it's an absolute scale. It's not an arbitrary starting spot, it's the absolute starting spot. So when we say Kelvin, it's not correct to say 0 degrees Kelvin. Now, the Kelvin scale and the Celsius scale are related in that one increment of Celsius, or Kelvin increment, one Kelvin temperature change is exactly the same as 1 degree change in Celsius. All right, so therefore, if that's true, once we get to this spot right here, we'll be at 273 Kelvin. So 0 degrees Celsius is 273 Kelvin. All right, that's because that's the coldest temperature that anything can get. And then we can keep on going up above too as well, and then theoretically no limit as to how high you can get on that scale. Now, that being said then, what would be the coldest temperature in Celsius that we could get? Well, that's going to then be minus 273. So that's the coldest Celsius temperature possible. And that will translate into minus 460 degrees Fahrenheit. So those are the coldest temperatures possible. 0 Kelvin in the absolute scale, or minus 273 on the Celsius scale, or a minus 460 degrees on the Fahrenheit scale. That means that all molecular motion comes to a stop and you can't get any colder. Now, these formulas right here are what we use to convert from one to the other. The easiest one, of course, is going to be to convert from Celsius to Kelvin or Kelvin to Celsius. Notice there's no degree symbol in the K there. If I take my Celsius temperature, I simply have to add 273, converts it into Kelvin. To convert from Celsius into Fahrenheit or Fahrenheit into Celsius, we got to use a ratio of the degrees of Celsius to Fahrenheit, either 5 to 9 or 9 to 5. So if I want to convert from Fahrenheit to Celsius, I first got to subtract 32 and then multiply it times 5/9. If I want to convert from Celsius to Fahrenheit, I'll first have to multiply it times 9/5 and then add 32 to it. All right, so that's how we could convert from one scale to the other. On the test in the next couple of weeks, we'll have to do a little bit of temperature conversion. We'll do some practice on it. All right, let's take a look at some common temperatures that we might encounter. All right, now looking at the second one here, 32 degrees Fahrenheit, we already talked about that, translates into 0 degrees Celsius. All right, they're both freezing temperature. That's the temperature at which water freezes, All right, now 0 Fahrenheit is not going to be any particular temperature. It was sort of the coldest artificially produced temperature at one point in time, and that translates into a negative 17.8 degrees Celsius. Now, number 3 here is kind of a special temperature. This is often known as room temperature. All right, room temperature. Now, when we say room temperature, well, that depends on what you have your thermostat set at. Most people set it at around 68 degrees, so when you hear the term room temperature, that's the temperature that we're talking about. Now, some people like their houses a little bit warmer, some like it a little bit cooler, so that might not be true for everybody, but when we say room temperature, that's what we mean. All right, what does that translate into in Celsius? That's about 20 degrees. 20 degrees Celsius. Now, it sounds cold, 20 degrees, but in Celsius, that's pretty warm. 98 degrees is a special temperature. That is what's known as normal body temperature. All right, if you take a thermometer and put it in your mouth, and many of you have, you should read 98 degrees. If you have a fever, you'll probably be a little bit above that there, and that's one of the symptoms of the coronavirus, COVID-19, is that you run a temperature Human body temperature of about 102 and 103 is getting pretty dang high. Once you get up to about 104, that's a get to the hospital quick kind of situation. In degrees Fahrenheit, that is. In Celsius, that translates to 37 degrees. Number 5 is a special temperature. That's the temperature at which water boils. Water boils at 212 degrees Fahrenheit, and we talked about that already, and that in Celsius is what we have at 100. 100 degrees Celsius, water boils. So that translates to 212 degrees Fahrenheit. Now, how warm would you say 80 degrees Fahrenheit is? That is a typical nice sunny day in the summer, 80 degrees Fahrenheit. Convert that into Celsius, and we're talking about 26.7 degrees. All right, sounds kind of cold, but in Celsius, that's a very nice day. All right, so Celsius temperatures don't vary quite as quickly as, say, or as much as, say, Fahrenheit degrees, because room temperature is 20, and a nice sunny day is about 27, 26, 27 degrees. Only 6 degrees difference in Celsius means a lot. All right, means a lot. Now, 32 degrees Fahrenheit is a freezing temperature, but 32 degrees Celsius, nothing in particular about that one. All right, and then here's a few other ones too as well. A special temperature in Celsius is 100 degrees. Convert that into Kelvin, and you just add 273. So 100 plus 273 is 373. The temperature or that water boils. Oh, I see a mistake here. There should not be a degree symbol with the Kelvin. All right, Kelvin does not have degrees. All right, 32 degrees Celsius translates to 310. All right, those are some somewhat common temperatures. All right, let's review a little bit. If I say room temperature, what temperature am I talking about? Room temperature. That would be 68 degrees Fahrenheit or 20 degrees Celsius. Room temperature. Now that depends on how much you want your thermostat at, but when we say that, that's typically what we mean. What would the temperature be of your normal body temperature? In Fahrenheit, 98. In Celsius, 37. What temperature does water boil at or melt at? Melt or freeze is going to be the same temperature. All right, that is going to be 32 in Fahrenheit, 0 in Celsius. 0 in Celsius. Now, when we say normal boiling or melting temperature, there's reasons why it could change. We'll see here that in a minute. What's the normal boiling temperature then? That would be your 100 Celsius or 212 Fahrenheit. Fahrenheit. Right? These are some key temperatures that you want to try to remember. All right, you'll run into them quite a bit. All right, how hot is something when it boils? How hot is something water when it freezes? Now it had to say water because other substances freeze and melt at different temperatures. By normal, there's reasons why that could actually change. Pressure, mixtures, all kinds of stuff like that. We'll talk about later. All right, one last thing, vaporization. In order for water or any liquid to go from a liquid to a gas, molecules have to jump off the surface. Now, what's going to be required for that to happen? Remember when we talked about water last semester, water has a plus and a minus end to it. And the pluses and minuses can attract to each other. We call that a hydrogen bond. And it makes the water molecules kind of stick together. And it gives rise to certain properties like why water has surface tension and water bugs can walk on water. Or waters can make droplets and stay in little balls. Or you can float a penny or a paperclip on that because of the surface tension. That's because of the sticking togetherness of the water molecules there. They're not extremely strongly stuck together, but there is an attraction to them. And in order for a liquid to vaporize, you have to break free of that intermolecular forces like that. So that's what it means when you vaporize, or what it takes to vaporize something. All right. Now, When water does vaporize, it goes from the liquid into the gas and becomes part of the air. Now, remember we talked about what air is made of. Air is a mixture of gases, mostly nitrogen and some oxygen and tiny amounts of other stuff like carbon dioxide, helium, methane, etc. All right, but mostly nitrogen and oxygen. And each one of them contributes a certain amount of pressure to the total pressure of the atmosphere, which at sea level would be about 101.3 kilopascal. All right, and we call these all partial pressures. Add them all up, and you get the pressure of everything together. Now, when water tries to vaporize, it sort of, comes off the surface and sort of has to push against the pressure that the air is putting down on it, like that. And the warmer the water is, the more vaporizes. So the vapor pressure from the water will increase with temperature. So looking at this graph right here, as the temperature goes up, the vapor pressure from water also goes up, like that. Eventually, at some point, this vapor pressure will equal the atmospheric pressure above it, and that is the temperature at which water is going to boil. When the vapor pressure equals the atmospheric pressure, that temperature is the temperature at water boils. So if the atmospheric pressure changes, and it does because of variations in weather and altitude and stuff, that's going to have an impact on the temperature at which water boils. All right, that will be the next thing that we talk about.